So, here's something that might keep you up at night, except tonight we're going to let it do the opposite. We're going to let it ease you into sleep, because there's something strangely comforting about the biggest mystery in the universe. And I mean that literally. The biggest mystery. Not the biggest unsolved crime, not the deepest part of the ocean we haven't mapped yet, but the actual, physical, measurable mystery of what most of the universe is made of. Because here's the thing, and this is where it starts to get interesting before we've even really begun. Most of the stuff in the universe, the overwhelming majority of the matter out there, is something we have never seen, never touched, never caught in a jar, never detected directly in any laboratory on Earth. We know it's there. We're almost certain it's there. The math demands it, the galaxies depend on it, and the entire structure of the cosmos, as we observe it, falls apart without it. And yet, we don't know what it is. Not really. Not yet. That's dark matter. And tonight we're going to walk through the whole story of how we figured out it exists, why we believe in something we can't see, what it might be, and why it matters. Not just to physicists, but to you, lying there in the dark, made of atoms, on a planet held together by gravity, in a galaxy that literally would not hold its shape without this invisible something threaded through it like scaffolding you can't touch. But let's not rush. Let's start where all good stories start, which is with someone noticing something strange and not being able to let it go. The year is 1933. The place is Zurich, and the person is a man named Fritz Zwicky. Now, Zwicky is one of those figures in the history of science who deserves to be way more famous than he is. He was a Swiss-born astronomer working at Caltech, and he was brilliant, but he was also, by almost every account, incredibly difficult to work with. Combative, blunt, sometimes outright rude. He reportedly called some of his colleagues spherical bastards, which, and this is kind of wonderful, he explained by saying they were bastards no matter which direction you looked at them from. That's the kind of person Fritz Zwicky was. He made enemies easily. But he also saw things other people missed. And in 1933, he saw something that would take the rest of the scientific world decades to fully appreciate. Zwicky was studying a cluster of galaxies. Not a single galaxy, but a whole group of them. The Coma Cluster, about 320 million light-years away. A massive collection of over 1,000 galaxies all bound together by gravity. And what Zwicky did was straightforward, at least in concept. He measured how fast the galaxies in the cluster were moving. He looked at the light coming from each galaxy, checked how much that light was shifted toward the red or blue end of the spectrum, which tells you whether something is moving toward you or away from you, and how fast. And he used those speeds to figure out how much mass the cluster must contain in order to hold itself together. Think of it this way. Imagine you're watching a merry-go-round spinning, and you can see the horses on the outside edge whipping around really fast. You know from basic physics that something has to be holding those horses on, some force, some structure. The faster they're spinning, the stronger that force has to be. If the horses are going incredibly fast, and the merry-go-round isn't flying apart, then there must be a lot of structural strength there, a lot of mass anchoring everything. That's essentially what Zwicky did with the Coma Cluster. He measured the speeds, and then he asked, how much mass does this cluster need to keep all these galaxies from flying off into the void? And the answer was shocking. The cluster needed about 400 times more mass than what he could account for by looking at all the visible galaxies. 400 times. That's not a small discrepancy. That's not a rounding error. That's like weighing your suitcase at the airport and being told it weighs 400 times what you expected. Something was deeply, fundamentally off. Zwicky called this missing stuff dunkle Materie, dark matter. And here's where the human story gets a little bittersweet, because almost nobody paid attention. Partly because Zwicky's personality had alienated so many of his peers, and partly because the measurement techniques of the 1930s were rough enough that people could wave the result away. Maybe his velocity measurements were off. Maybe the cluster wasn't really gravitationally bound in the way he assumed. There were enough escape hatches that the scientific community could shrug and move on. And they did, for about 40 years. Now, that's a long time to ignore a clue that big. But science does this sometimes. A result comes along that's too strange, too inconvenient, too far ahead of the tools available to confirm it, and it just sort of sits there in the literature, waiting. Zwicky kept working. He did extraordinary things, actually, including some of the earliest work on supernovae and gravitational lensing. But the dark matter idea gathered dust. He died in 1974, and by that point the revolution was just barely beginning, sparked by someone very different from Zwicky in almost every way. Her name was Vera Rubin. And if Zwicky is the irascible genius who got there first and was ignored, Rubin is the quiet, persistent observer who built the case so carefully and so thoroughly that the world could no longer look away. Rubin grew up in Washington, D.C., fascinated by the stars from childhood. She wanted to study astronomy, but the path wasn't easy. When she applied to Princeton's graduate program in the early 1950s, she was told that women were not admitted. Just flat out, no. She ended up at Cornell and then Georgetown, and she carved out a career in a field that was, at the time, almost entirely male and not particularly welcoming to her. But here's what Rubin had that made all the difference. She was a meticulous observer, and she had access to increasingly powerful tools. By the late 1960s and into the 1970s, she was working with an instrument maker named Kent Ford, who had built an extraordinarily sensitive spectrograph, a device that could measure the light from distant objects with much greater precision than earlier instruments. And Rubin and Ford turned this instrument on spiral galaxies. Not clusters of galaxies, like Zwicky had studied, but individual galaxies, those beautiful pinwheel shapes you've seen in photographs, with arms of stars sweeping out from a bright central core. What Rubin and Ford were measuring was the rotation speed of these galaxies, how fast the stars at different distances from the center were orbiting. And here's what everyone expected to find. If you think about our solar system, Mercury, the closest planet to the Sun, orbits the fastest. Neptune, way out at the edge, orbits much more slowly. This makes intuitive sense. The Sun's gravity is strongest close in and weaker farther out, so things close to the center move fast, and things far away move slow. This pattern is called Keplerian rotation, after Johannes Kepler, who worked out the laws of planetary motion back in the early 1600s, and astronomers expected spiral galaxies to behave the same way. Most of the visible mass, the stars, the gas, the glowing stuff, is concentrated toward the center of a galaxy. So stars near the center should orbit fast, and stars out in the suburbs, far from the bright core, should orbit much more slowly. That's not what Rubin found. What she found, galaxy after galaxy, was that the rotation curves were flat. The stars far out from the center were moving just as fast as the stars close in. In some cases, the outer stars were moving even faster than expected. And this was not a subtle effect. It was dramatic, consistent, and it showed up in galaxy after galaxy after galaxy. By the time Rubin and Ford had measured dozens of spiral galaxies, the pattern was unmistakable. Think about what that means for a second. If the stars on the outskirts of a galaxy are moving that fast, and the only gravity holding them in orbit comes from the visible matter you can see, the stars and gas concentrated in the middle, then those outer stars should be flying off into intergalactic space. They're moving too fast for the visible matter to hold on to them. It's like watching a car take a curve at 200 miles an hour on a road that should only support 60. The car should skid off the road. The stars should fly away, but they don't. They stay in their orbits, calm as anything, as if something invisible is holding them in place. And that something, Rubin argued, was dark matter. Not concentrated in the center of the galaxy where the visible stuff is, but spread out in a vast, invisible halo surrounding the entire galaxy, extending far beyond the visible stars, providing the extra gravitational pull needed to keep everything spinning at those unexpectedly high speeds. Now, Rubin was careful. She was rigorous. She published her results methodically, and she let the data speak. But even so, there was resistance. Some people suggested that maybe our understanding of gravity was wrong at large scales. Maybe Newton's laws, which work perfectly well for apples and planets, and most things we encounter, break down when you're talking about something as large as a galaxy. That's actually not a crazy idea, and we'll come back to it later because it leads to some genuinely interesting alternative theories. But for most of the physics community, the simpler explanation, that there's extra mass out there that we can't see, started to gain traction. And here's something important to understand about why scientists were willing to accept the existence of something invisible. It's not actually that unusual in the history of science. We've done this before. In the 1840s, astronomers noticed that Uranus wasn't quite following the orbit that Newton's laws predicted. It was being tugged slightly off course by something. And rather than throw out Newton's laws, they predicted that there must be another planet out there, one they hadn't seen yet, whose gravity was doing the tugging. In 1846, they pointed a telescope at the spot where this unseen planet should be, and there it was. Neptune. A whole new world, discovered not by seeing it, but by noticing its gravitational effect on something else. Dark matter, in a sense, is the same kind of reasoning. We see its gravitational effects. We see galaxies spinning too fast, clusters holding together when they shouldn't, and, as we'll get into, we see the way light bends around massive objects in ways that require more mass than we can account for. The gravity is real. The effects are measurable. The question is just, what is the stuff that's causing it? And that question, as simple as it sounds, has turned out to be one of the hardest problems in all of physics. Because dark matter, whatever it is, doesn't interact with light. It doesn't glow. It doesn't reflect. It doesn't absorb. It doesn't cast shadows. It passes through ordinary matter like a ghost through a wall. You could have a stream of dark matter flowing through your body right now, and in fact, based on our best estimates, there probably is, and you would feel absolutely nothing. No warmth, no pressure, no tingle, nothing. It interacts through gravity and possibly through the weak nuclear force, and that's it, which makes it, from an experimental standpoint, almost impossibly hard to catch. But let's not get ahead of ourselves. We're still in the 1970s, and Vera Rubin's rotation curves are just starting to reshape how people think about the universe. What happened next was a slow accumulation of evidence from completely different directions. Evidence that kept pointing to the same conclusion, that kept saying the same thing in different languages. And the first of those independent lines of evidence came from a place you might not expect. The hot gas between galaxies, glowing in X-rays, telling a story about gravity and temperature and mass that matched what Rubin had been finding in individual galaxies, but on a much grander scale. So here's the setup. Galaxy clusters, as we talked about with Zwicky, are these enormous collections of hundreds or even thousands of galaxies, all bound together by gravity. And for a long time, the only way to study them was with optical telescopes. You'd look at the galaxies, count them up, estimate their masses, and try to figure out whether the cluster had enough gravitational pull to hold itself together. That's essentially what Zwicky did back in the 1930s, and he came up short by a factor of several hundred. But starting in the late 1960s and really picking up steam through the 1970s and 1980s, a new window opened up. X-ray astronomy. Now, X-rays from space can't reach the ground. Earth's atmosphere absorbs them, which is great for us. You don't want to be bathed in cosmic X-rays, but it means that if you want to study X-ray sources in the sky, you need to get above the atmosphere. Early X-ray astronomy used sounding rockets, brief suborbital flights that gave scientists just a few minutes of observation time before the instruments came back down. But then came dedicated X-ray satellites, and the game changed completely. The first major one was Uhuru, launched in 1970 from a platform off the coast of Kenya. The name means freedom in Swahili, and it was launched on Kenyan Independence Day, which is a lovely detail. Uhuru surveyed the entire sky in X-rays for the first time, and among the things it found were these diffuse, extended sources of X-ray emission centered on galaxy clusters. Not point sources, not individual stars or compact objects, but this broad, soft glow filling the space between the galaxies. And here's what that glow turned out to be. The space between galaxies in a cluster isn't empty. It's filled with an incredibly hot, incredibly thin gas, mostly hydrogen and helium, ionized into a plasma, heated to temperatures of tens of millions of degrees. At those temperatures, the gas emits X-rays. And when I say hot, I mean staggeringly hot. The gas between galaxies in a rich cluster can be 100 million degrees Kelvin. That's hotter than the center of the sun. And yet it's so diffuse, so spread out, that you'd never know it was there unless you had an X-ray telescope. In visible light, that space looks empty. In X-rays, it's glowing. Now, here's where this connects to dark matter, and it's beautifully simple in its logic. That gas is hot, extremely hot, and hot gas wants to expand. That's just basic thermodynamics. Think about steam escaping from a kettle. The hotter the gas, the faster the particles are moving, and the more desperately the gas wants to fly apart in every direction. So the question becomes, what's holding it in? What keeps this 100 million degree gas from just dispersing into the void? Gravity. The gravitational pull of the cluster is what holds the gas in place, keeps it confined in this enormous cloud surrounding and permeating the cluster. And because we can measure the temperature of the gas from its X-ray spectrum, and we can measure how the gas is distributed from the shape and brightness of the X-ray emission, we can actually calculate how much gravitational pull is needed to keep it there. It's a straightforward calculation, at least in principle. You know the temperature, you know the density profile, you apply the equations of hydrostatic equilibrium, which is just a fancy way of saying the outward pressure of the hot gas is balanced by the inward pull of gravity. And you get a number for the total mass of the cluster. And that number, every single time, came out way too high. Way higher than what you could account for with the visible galaxies and the hot gas combined. The hot gas itself actually contains more mass than all the galaxies in the cluster put together, which is kind of surprising on its own. Most of the ordinary matter in a cluster isn't in the galaxies, it's in this diffuse intergalactic medium. But even when you add the galaxies and the gas together, you still only get maybe 15% of the mass you need. The rest is invisible. The rest is dark. And this was coming from completely different physics than Rubin's rotation curves. Rubin was measuring the orbital speeds of stars in individual galaxies. The X-ray observations were measuring the temperature of gas in the spaces between galaxies and clusters. Different objects, different scales, different instruments, different equations, and yet they were converging on the same answer. There's a lot more mass out there than we can see. This is what scientists mean when they talk about independent lines of evidence, and it's one of the things that makes the case for dark matter so compelling. It's not just one observation that could be explained away as a measurement error or a peculiar galaxy. It's multiple, completely independent methods, all pointing in the same direction. And by the early 1980s, a third line of evidence was starting to emerge, one that Einstein himself had predicted decades earlier, though he probably never imagined it would be used for this purpose: gravitational lensing. Let's talk about that for a second, because it's one of the most beautiful ideas in all of physics, and it gives us one of the most direct ways to map out where dark matter actually is. So, general relativity tells us that mass curves space-time. You've probably heard that analogy about a bowling ball sitting on a rubber sheet. It creates a dip, and if you roll a marble nearby, the marble curves toward the bowling ball. That analogy has its limits, but it captures the essential idea. Mass warps the geometry of space around it, and things moving through that warped space follow curved paths. Now here's the key insight. Light follows those curved paths too. A beam of light passing near a massive object doesn't travel in a perfectly straight line. It bends, ever so slightly, following the curvature of space-time. Einstein worked this out in 1915, and it was famously confirmed during the solar eclipse of 1919, when Arthur Eddington measured the positions of stars near the sun and found they were slightly displaced from where they should have been, shifted because their light had been bent by the sun's gravity on its way to Earth. That confirmation made Einstein a worldwide celebrity overnight, which is a whole other story. But the point is, light bends around massive objects. Now, scale that up. Instead of the sun bending starlight by a tiny fraction of an arc-second, imagine an entire galaxy cluster. Millions of billions of solar masses sitting between you and a more distant galaxy. The light from that distant galaxy passes through the warped space-time around the cluster, and it bends. If the alignment is right, the distant galaxy gets distorted, stretched into arcs, or even complete rings. The cluster acts like a giant lens, focusing and distorting the light from objects behind it. That's gravitational lensing. And here's what makes it so powerful for studying dark matter. The amount of bending depends on the total mass of the lens. All the mass. Not just the luminous mass, not just the hot gas, but everything, including whatever invisible stuff might be there. So if you carefully measure the distortion of background galaxies, you can reconstruct the total mass distribution of the foreground cluster. You can make a map of where the mass is, and you can compare that map to where the visible matter is. And when people started doing this seriously in the 1980s and 1990s, the maps didn't match. The mass maps showed far more material than the light maps. There were huge concentrations of mass in places where there was relatively little visible matter. The lensing was telling the same story as the rotation curves and the X-ray gas. Something massive, something gravitationally significant was there. And it wasn't shining. One of the most spectacular demonstrations of this came later, in 2006, with an object called the Bullet Cluster. And this one deserves some real attention because a lot of physicists consider it the single most compelling piece of evidence for dark matter as an actual substance rather than a modification of gravity. The Bullet Cluster is actually two galaxy clusters that collided, or more accurately, passed through each other. And when galaxy clusters collide, something remarkable happens. The individual galaxies, which are relatively small and far apart, pass through each other like two swarms of bees flying through one another. They barely interact. But the hot gas in each cluster, that diffuse X-ray emitting plasma we were just talking about, that gas does interact. It collides, it shocks, it heats up, it slows down. Think of it like two clouds of steam slamming into each other. The gas piles up in the middle. So after the collision, you have this separation. The galaxies have sailed through to the other side, but the gas, which is the majority of the ordinary, visible matter, is stuck in the middle, lagging behind. Now, if you look at the bullet cluster in X-rays, you see the gas concentrated between the two subclusters. That's where most of the normal matter is. But when you do the gravitational lensing analysis, when you map where the mass actually is based on how it bends the light from background galaxies, the mass isn't centered on the gas. The mass is centered on the galaxies. The mass has kept going, passed right through, just like the galaxies did. Think about what that means. The bulk of the mass in this system is not where the bulk of the ordinary matter is. The mass is somewhere else, and it behaved during the collision exactly the way you'd expect something to behave if it doesn't interact with ordinary matter except through gravity. It passed right through, unimpeded, like a ghost through a wall. The gas got stuck because gas interacts with other gas. The dark matter didn't get stuck because dark matter doesn't interact with gas or with itself in any significant way beyond gravity. It just kept going. This is incredibly hard to explain with modified gravity theories. If you try to account for the bullet cluster by tweaking the laws of gravity rather than invoking dark matter, you run into a wall because the gravitational lensing mass is clearly separated from the visible mass. The gravity isn't coming from where the visible stuff is, it's coming from somewhere else. Something invisible has its own location, its own distribution, independent of the gas and stars. That really does sound like a substance. That sounds like stuff. Particles, material. Something with mass that occupies space and moves through the universe and interacts gravitationally, but otherwise ignores everything else. Now, I should be fair here. Modified gravity theories haven't been completely ruled out by the bullet cluster alone, and there are some very clever theorists who have tried to construct models that can accommodate it. Science is never quite as neat as we'd like it to be, but the bullet cluster made a lot of fence-sitters come down on the side of dark matter as a real physical substance. It was that convincing. And by this point in the story, let's say the mid-2000s, you had this convergence of evidence from galaxy rotation curves, from X-ray observations of cluster gas, from gravitational lensing, and from one more source that we haven't talked about yet, one that might be the most precise and surprising of all. It comes not from galaxies or clusters, but from the very earliest light in the universe, a faint glow that has been traveling through space for over 13 billion years, carrying in its subtle patterns a record of what the universe looked like when it was only about 380,000 years old. That light has a name, and you've probably heard it before: the cosmic microwave background. And the story of how it was discovered is one of those beautiful accidents in the history of science, the kind where two people stumble onto something monumental while trying to do something completely different. It's 1964, and we're at Bell Labs in Holmdel, New Jersey. Arno Penzias and Robert Wilson are radio astronomers, and they've got access to this remarkable piece of equipment, a large horn antenna originally built for satellite communication experiments. It's shaped almost like a giant ear, this big funnel of metal designed to pick up very faint microwave signals bouncing off early communication satellites. The satellite work is winding down, and Penzias and Wilson want to repurpose the antenna for radio astronomy to study signals from our own galaxy. But before they can do any real science with it, they need to calibrate the thing, which means they need to account for every possible source of noise, every stray signal, every bit of interference, so they can subtract it all out and be left with just the signal they're looking for. And here's where the trouble starts. No matter what they do, they can't get rid of this persistent low-level hiss. It's faint, but it's there, and it's everywhere. They point the antenna at New York City. Maybe it's picking up radio interference from the city. Nope, the hiss doesn't change. They point it at different parts of the sky, different times of day, different seasons. The hiss is the same in every direction. It's isotropic, meaning it's completely uniform across the entire sky. That's strange, because most sources of radio noise, a city, a star, a satellite, come from a specific direction. This is coming from everywhere equally. They start troubleshooting. Maybe it's the antenna itself. They crawl inside the horn and find that pigeons have been nesting in there, and the inside is coated with what Penzias later delicately referred to as a white dielectric material. Pigeon droppings, in other words. They clean it out. They trap the pigeons and release them 30 miles away. The pigeons come back, because pigeons are like that. They eventually have to deal with the pigeons more permanently, which is a sad little footnote to one of the greatest discoveries in cosmology. But even after all that, the hiss is still there. Same intensity, same everywhere, same always. It corresponds to a temperature of about 3.5 Kelvin, just a few degrees above absolute zero. Very cold, very faint, very persistent. Now, here's the beautiful part. Just 30 miles away at Princeton University, a group of physicists led by Robert Dick and Jim Peebles have been working on a theoretical prediction. They've calculated that if the Big Bang really happened, if the universe really did begin in an incredibly hot, dense state and has been expanding and cooling ever since, then there should be a leftover glow from that early heat, stretched by the expansion of the universe from its original scorching temperatures down to just a few degrees above absolute zero. They've even started building their own antenna to look for it. And then they get a phone call from Penzias and Wilson, who are basically saying, "Hey, we've got this annoying noise we can't get rid of. Do you have any idea what it might be?" And Dickie hangs up the phone and reportedly turns to his colleagues and says, "Boys, we've been scooped. That noise, that hiss, that stubborn signal that wouldn't go away no matter how many pigeons they evicted. That was the cosmic microwave background, the afterglow of the Big Bang itself, light that was emitted when the universe was about 380,000 years old, when it had cooled just enough for atoms to form for the first time, when the primordial plasma became transparent and released all the photons that had been bouncing around inside it. Those photons have been traveling through space ever since, getting stretched by the expansion of the universe from visible light all the way down to microwaves, cooling from thousands of degrees to about 2.725 Kelvin. And they fill the entire sky, uniformly, in every direction. That's what Penzias and Wilson found. Now, at first glance, this might seem like it's about the Big Bang, not about dark matter. And you're right, The initial discovery was really about confirming that the universe had a hot beginning. Penzias and Wilson won the Nobel Prize for it in 1978. But here's where it gets relevant to our story, and this is where you need to think about what that ancient light is actually telling us. The cosmic microwave background is almost perfectly uniform. Almost. But not quite. And those tiny imperfections, those minuscule variations in temperature from one patch of sky to another, turn out to be one of the most powerful tools we have for understanding what the universe is made of, including how much dark matter there is. Think about it this way. When the universe was very young, less than 380,000 years old, it was a hot, dense soup of particles and radiation. Protons, electrons, photons, all smashing into each other constantly. And in this soup, there were tiny variations in density. Some regions were just slightly denser than others. These density variations had been seeded even earlier, during the very first moments of the universe, probably during a period called inflation. In the denser regions, gravity was trying to pull matter inward, compressing it. But the photons, the light trapped in this plasma, were pushing back, creating pressure that resisted the compression. So you got this tug-of-war, gravity pulling in, radiation pressure pushing out, and the result was oscillations, sound waves, essentially, pressure waves rippling through the primordial plasma at incredible speeds. Now, here's where dark matter enters the picture. Remember, dark matter doesn't interact with light. It doesn't feel radiation pressure. So while ordinary matter, protons, electrons, the stuff that does interact with photons, is sloshing back and forth in these acoustic oscillations, dark matter is just sitting there in the gravitational wells, not oscillating, not bouncing around. It's providing extra gravitational pull, deepening the wells that ordinary matter falls into. But it's not participating in the pressure waves. It's like, imagine a swimming pool with waves sloshing back and forth. And then imagine there are heavy weights bolted to the bottom of the pool that don't move with the water, but do affect how the water flows. The dark matter is the weights. The ordinary matter is the water. And this difference, this distinction between matter that oscillates with the photons and matter that doesn't, leaves a very specific signature in the cosmic microwave background. When you map the tiny temperature fluctuations across the sky and analyze them statistically, breaking them down by angular scale, you get a pattern called the power spectrum. It's a graph that shows how much variation there is at different sizes, and it has a series of peaks and troughs. The positions and heights of those peaks encode an extraordinary amount of information about the composition of the universe. The ratio of the first peak to the second peak, for instance, tells you the ratio of ordinary matter to dark matter. The first peak is enhanced by all matter, ordinary and dark, falling into gravitational wells. The second peak is suppressed because it represents a phase of the oscillation where radiation pressure is pushing matter back out of the wells, and only ordinary matter participates in that rebound. Dark matter stays put, so it doesn't contribute to the second peak the same way. This is genuinely remarkable. By measuring the relative heights of bumps in a graph of microwave temperature variations across the sky, you can figure out how much of the universe is made of ordinary atoms and how much is made of something else entirely. And the answer, when you work it all out, is striking. Ordinary matter, protons, neutrons, electrons, everything that makes up you and me and stars and planets and gas clouds accounts for only about 5% of the total energy content of the universe. Dark matter accounts for about 27%. And the remaining 68% is something even more mysterious, called dark energy, which we'll get to later. But focus on those numbers for a moment. For every kilogram of ordinary matter in the universe, there are roughly 5 kilograms of dark matter. It's not a small correction. It's the dominant form of matter. The first really detailed measurements of the CMB power spectrum came from a series of increasingly sophisticated experiments. The COBE satellite, launched in 1989, was the first to detect the tiny temperature fluctuations, the anisotropies, in the cosmic microwave background. George Smoot and John Mather led that mission, and they won the Nobel Prize in 2006 for the results. COBE showed that the fluctuations were there at a level of about 1 part in 100,000, incredibly faint. But the resolution wasn't good enough to map out the detailed peak structure. That came next, with experiments like Boomerang and Maxima around the year 2000. These were balloon-borne instruments flown high in the atmosphere to get above most of the water vapor that absorbs microwaves. They mapped smaller patches of sky but with much finer resolution, and they nailed down the position of the first acoustic peak, which told us that the universe is geometrically flat. And then came WMAP, the Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001. WMAP mapped the full sky with enough precision to measure multiple acoustic peaks, and its results were transformative. The data fit a model with about 4.5% ordinary matter, about 23% dark matter, and the rest, dark energy. These numbers were consistent with everything else: the rotation curves, the cluster dynamics, the lensing. But they came from a completely independent method, from the physics of sound waves in a plasma that existed when the universe was less than 500,000 years old. And then, in 2009, the European Space Agency launched Planck, which was even more precise. Planck measured the CMB power spectrum with such exquisite accuracy that it pinned down the cosmological parameters to within fractions of a percent. The Planck results, published in 2013 and refined in 2015 and 2018, gave us the numbers I quoted earlier: about 5% ordinary matter, 27% dark matter, 68% dark energy. These are now the standard values, the concordance cosmology, and they come from fitting the detailed shape of those acoustic peaks to theoretical models. So now you have 4 completely independent lines of evidence: galaxy rotation curves, X-ray gas in clusters, gravitational lensing, and the cosmic microwave background, all pointing to the same conclusion. There is far more matter in the universe than we can see, and it doesn't interact with light. 4 different methods, 4 different physical phenomena, 4 different epochs of cosmic history, and they all agree. That kind of convergence is rare in science, and it's the reason most physicists and astronomers are confident that dark matter is real, even though no one has ever directly detected a dark matter particle in a laboratory. The indirect evidence is overwhelming. But of course, knowing that dark matter exists and knowing what it actually is are 2 very different things. And by the time the CMB measurements were confirming the cosmic abundance of dark matter with stunning precision, particle physicists had already been thinking hard about what kind of particle it might be, and they had some very specific ideas. Candidates, you might call them, with names that sound like they belong in a science fiction novel. The leading candidate for decades has been something called a WIMP, which stands for Weakly Interacting Massive Particle, And that name actually tells you almost everything you need to know about the idea. It's a particle that has mass, so it pulls on things gravitationally, just like dark matter should. And it interacts weakly, meaning it barely talks to ordinary matter at all. Not through electromagnetism, not through the strong nuclear force, just through gravity and possibly through the weak nuclear force, which is the same force responsible for certain kinds of radioactive decay. And that weakly interacting part is exactly why dark matter is so hard to detect directly. It's not that dark matter is hiding from us out of spite. It's that the physics of whatever it's made of simply doesn't allow it to engage with photons, with light, with the electromagnetic force that governs almost everything we experience in daily life: color, reflection, absorption, emission, opacity, transparency. All of those are electromagnetic phenomena. If a particle doesn't participate in electromagnetism, it's invisible. Period. It won't glow, it won't cast a shadow, it won't bounce off a mirror. It'll just drift right through matter like matter isn't even there. And here's the thing that made WIMPs so attractive to physicists starting in the late 1970s, and especially through the 1980s and 1990s. It wasn't just that they fit the observational requirements for dark matter. It was that particle physics independently predicted that particles like this should exist for completely unrelated reasons. This is sometimes called the WIMP miracle, and it's worth understanding because it drove an enormous amount of research and funding for decades. So let me walk you through it. In the standard model of particle physics, which is the framework that describes all the known fundamental particles and forces, there are some well-known problems, things the model can't explain. One of the big ones is called the hierarchy problem, which has to do with why the Higgs boson has the mass it does. The Higgs was finally discovered at CERN in 2012, and its mass is about 125 billion electron volts, which in the units physicists use is relatively light. The problem is that when you do the quantum mechanical calculations, the Higgs mass should get enormous corrections from virtual particles at very high energies, corrections that would push it up to something like the Planck scale, which is roughly 10 to the 19th billion electron volts. That's a factor of about 10 to the 17th too big. So either there's an absurdly precise cancellation happening, which physicists find deeply unsatisfying, like balancing a pencil on its tip and having it just stay there, or there's some new physics that naturally keeps the Higgs mass small. The most popular solution for a long time was called supersymmetry, often shortened to SUSY. The idea is elegant in a mathematical sense. For every known particle, there exists a heavier partner particle. Electrons get selectrons, quarks get squarks. Yes, those are the real names. Photons get photinos, and so on. These partner particles would cancel out those dangerous quantum corrections to the Higgs mass in a very natural way. And here's where it connects to dark matter. In many versions of supersymmetry, the lightest of these new partner particles is stable. It can't decay into anything lighter. And it turns out to be electrically neutral, meaning it doesn't interact with light. It would be massive, probably somewhere between 10 and 1,000 times the mass of a proton, and it would interact only through gravity and the weak force. In other words, it would be a WIMP, a perfect dark matter candidate, falling right out of a theory that was invented to solve a completely different problem. But the miracle goes even further. If you calculate how many of these particles would have been produced in the early universe, in the hot, dense conditions right after the Big Bang, and then figure out how many would survive as the universe cooled and expanded, you get a number that's remarkably close to the observed density of dark matter. This is the WIMP miracle proper. The fact that a particle with weak force-scale interactions and a mass in the 100 giga-electron-volt range naturally produces the right cosmic abundance. It felt too good to be a coincidence. It felt like the universe was practically handing physicists the answer. So starting in the 1980s and really accelerating through the 1990s and 2000s, an enormous experimental effort was launched to find WIMPs. And this effort took three complementary approaches, which physicists sometimes call the three legs of the stool. The first approach is direct detection. The idea is straightforward in principle, even if it's nightmarishly difficult in practice. If WIMPs are real, then they're everywhere, streaming through the galaxy, through the solar system, through the Earth, through you, right now as you lie there. Billions of them passing through your body every second, and almost none of them hitting anything because they interact so weakly. But almost none isn't zero. Very rarely, a WIMP should collide with an atomic nucleus, and if you build a sensitive enough detector, you might catch that collision. The recoiling nucleus would deposit a tiny amount of energy. We're talking about the energy equivalent of a few kilo-electron volts, which is almost nothing. And you'd need to distinguish that faint signal from all the background noise caused by cosmic rays, natural radioactivity in the rocks around you, radon gas, even the radioactivity in the detector materials themselves. So what do? You go deep underground, where the rock above you shields against cosmic rays. You build your detector out of the most radio-pure materials you can find. You surround it with layers of shielding, lead, copper, water, and you wait. Some of the most famous experiments in this category include DAMA at the Gran Sasso National Laboratory in Italy, which has been running since the late 1990s. Xenon, also at Gran Sasso, which uses liquid xenon as its detection medium. LOX, which operated in the Sanford Underground Research Facility in South Dakota, nearly a mile below the surface in an old gold mine. And its successor, LUX Zeppelin, or LZ, which started taking data around 2022. There's also Panda X in China, operating deep beneath the Jinping Mountains with over 2 kilometers of rock overhead, the deepest underground laboratory in the world. These experiments have gotten extraordinarily sensitive over the years. The current generation can detect energy deposits so small that they're bumping up against a fundamental background called the neutrino floor, the point where neutrinos from the sun and from cosmic sources start producing signals that look just like WIMP collisions. And yet, despite decades of searching, none of these experiments has produced a confirmed WIMP detection. DAMA has claimed a signal for years. They see an annual modulation in their event rate that they attribute to the Earth's motion through the galaxy's dark matter halo. But no other experiment has been able to reproduce it, and the physics community remains deeply skeptical. It's one of the more frustrating controversies in the field. The second approach is indirect detection. Instead of waiting for a WIMP to hit a nucleus in your lab, you look out into space for signs that WIMPs are annihilating with each other. If WIMPs are their own antiparticles, which many theoretical models predict, then when two of them meet, they should annihilate and produce a shower of ordinary particles: gamma rays, positrons, antiprotons, neutrinos. You'd expect these annihilations to happen most frequently where dark matter is densest, in the centers of galaxies, in dense clumps, maybe even in the cores of stars. So experiments like the Fermi Gamma Ray Space Telescope, launched in 2008, have been scanning the sky for excess gamma rays coming from places where you'd expect dark matter to be concentrated. The Alpha Magnetic Spectrometer on the International Space Station has been looking for excess positrons in cosmic rays. IceCube, that incredible detector buried in a cubic kilometer of Antarctic ice, has been searching for high-energy neutrinos that might come from WIMP annihilations in the Sun's core, where dark matter particles could accumulate over billions of years. There have been tantalizing hints. Fermi detected an excess of gamma rays coming from the center of the Milky Way, the so-called galactic center excess, and for a while, some physicists thought it might be a dark matter signal. But more recent analyses suggest it's probably caused by a population of millisecond pulsars, rapidly spinning neutron stars, that are too faint to resolve individually. The AMS experiment found more positrons in cosmic rays than expected, which could be dark matter annihilation, but could also be explained by nearby pulsars. Every time there's a hint, there's an astrophysical explanation that's at least as plausible. It's maddening. The third approach is to try to make dark matter in a particle accelerator. If WIMPs have masses in the range that theory predicts, then the Large Hadron Collider at CERN should have enough energy to produce them. You'd smash protons together at enormous energies, and occasionally, among the debris, you might create a pair of dark matter particles. You wouldn't see them directly. They'd escape the detector without a trace. But you'd notice that some energy and momentum went missing from the collision. You'd add up everything you could see, compare it to what went in, and find that the books don't balance. Missing energy is the signature. The LHC has been searching for this since it started running at full power around 2010, and especially after its energy upgrade in 2015. The ATLAS and CMS detectors have looked at billions upon billions of collisions, and they've found nothing. No missing energy beyond what the standard model predicts. No supersymmetric particles. No WIMPs. The LHC did find the Higgs boson in 2012, which was a triumph. But that was the last piece of the standard model, not new physics beyond it. The absence of supersymmetric particles at the LHC has been genuinely shocking to many theorists who expected them to show up. It hasn't killed supersymmetry entirely. You can always push the predicted masses higher, beyond the LHC's reach. But it has seriously dented the WIMP miracle's appeal. If supersymmetry exists, it's not in the simple, natural forms that made it so attractive in the first place. So by the mid-2000s, the field found itself in a strange position. The evidence for dark matter was stronger than ever. Planck had nailed down the cosmic abundance. The bullet cluster was sitting there like a smoking gun. Rotation curves were textbook material. But the leading particle candidate, the WIMP, was increasingly looking like it might not pan out. Not definitively ruled out, but squeezed into ever smaller corners of parameter space. And that opened the door for other candidates that had been waiting in the wings, some of them for decades. One of the most intriguing is the Axion. And the Axion has a backstory that's almost as beautiful as the WIMP miracle, because like the WIMP, it was invented to solve a completely different problem in particle physics, one that has nothing to do with dark matter at all. The problem is called the strong CP problem, and it has to do with a deep symmetry puzzle in quantum chromodynamics, the theory of the strong nuclear force. Here's the gist. The equations of QCD contain a term that, if it were non-zero, would cause the neutron to have a measurable electric dipole moment. Basically, the positive and negative charges inside the neutron would be slightly offset. Experiments have looked for this with extraordinary precision. And the neutron's electric dipole moment is either zero or so incredibly tiny that it's indistinguishable from zero. And that's the puzzle, because there's no obvious reason why it should be zero. The parameter that controls this, physicists call it theta, could in principle be any value between 0 and roughly 2 pi. It's like a dial. And if you just randomly set that dial, the odds of landing exactly on 0 are essentially nil. Yet nature seems to have set it to 0. or at least to something smaller than about 10 to the minus 10. That's not just small, that's absurdly, suspiciously small. And in physics, when a number that could be anything turns out to be almost exactly zero, that usually means something deeper is going on. There's usually a reason. Think about it this way. Imagine you walk into a room and there's a spinning top balanced perfectly on its point. Not wobbling, not falling over, just sitting there motionless on the very tip. You'd immediately think, okay, something is holding it there. Some mechanism, some trick I'm not seeing. Because the odds of it just happening to be perfectly balanced by accident are basically zero. That's the strong CP problem in a nutshell. The theta parameter is balanced on a knife's edge, and nobody could explain why. Now, people tried various approaches. One idea, proposed in the mid-1970s, was that maybe one of the quarks, the up quark specifically, was actually massless. If the up quark had exactly zero mass, then theta could be rotated away through a mathematical redefinition, and the problem would dissolve. It was elegant, but lattice QCD calculations eventually showed pretty convincingly that the up quark does have a non-zero mass, so that escape hatch closed. And then, in 1977, Roberto Pache and Helen Quinn proposed something genuinely brilliant. They said, what if theta isn't a fixed parameter at all? What if it's a dynamical field, something that can adjust itself? They introduced a new symmetry into the theory, now called Peck-Quinn symmetry. And when this symmetry is spontaneously broken, the theta parameter effectively becomes a field that naturally relaxes to zero. It's like replacing that impossibly balanced spinning top with a ball at the bottom of a bowl. No matter where you start the ball, it rolls down to the lowest point. The strong CP problem just solves itself. Theta goes to zero dynamically, not by accident, but because the physics drives it there. Here's the thing, though. Whenever you spontaneously break a global symmetry in quantum field theory, you get a new particle, a light boson associated with the broken symmetry. This is a deep result, connected to something called Goldstone's theorem. And in 1978, two physicists independently worked out what this new particle would look like. Steven Weinberg, yes, the same Weinberg who won the Nobel Prize for electroweak unification, and Frank Wilczek, who would later win his own Nobel for work on the strong force, both published papers describing this new hypothetical particle. Wilczek named it the Axion, after a brand of laundry detergent, because it cleaned up the strong CP problem, which is honestly one of the best particle names in all of physics. So what is the Axion, exactly? It's predicted to be extraordinarily light, far lighter than a WIMP, potentially billions or even trillions of times lighter than an electron. It interacts with ordinary matter so feebly that it makes neutrinos look sociable. It has no electric charge. It barely interacts through any of the known forces. And yet, if axions exist with the right mass and were produced in the right quantities in the early universe, they could account for all of the dark matter. And this is where the story gets really interesting, because the way axions would have been produced as dark matter is completely different from how WIMPs would have been produced. Remember, WIMPs are thermal relics. They were in thermal equilibrium with the hot plasma of the early universe, bouncing around, annihilating, being created until the universe cooled enough that they froze out. Axions don't work like that at all. They're too weakly interacting to have ever been in thermal equilibrium. Instead, the leading production mechanism is something called vacuum misalignment, and it's one of those ideas that sounds abstract but is actually quite intuitive once you sit with it. Here's the picture. In the very early universe, when temperatures were extraordinarily high, the Pecky-Quinn symmetry was unbroken. As the universe cooled past a certain critical temperature, the symmetry broke, and the Axion field settled into some initial value, some random starting point on its potential. But at that early time, the Axion mass was effectively zero because of high temperature effects. The field just sat there at whatever value it started at, frozen in place. Then, as the universe continued to cool, the Axion mass gradually turned on. And once the mass became significant, once the curvature of the bowl, so to speak, became steep enough, the Axion field started to oscillate around the minimum of its potential, back and forth, like a ball rolling back and forth in that bowl. Now here's what's wild. Those coherent oscillations of the Axion field behave, from a cosmological perspective, exactly like cold, dark matter. They carry energy, they dilute with the expansion of the universe in the same way that matter does, and they don't move fast. They're cold, in the cosmological sense. So you get a universe filled with this oscillating field that gravitates just like dark matter should. It's not individual particles zipping around. It's more like a vast, gentle wave permeating all of space. Though you can also think of it as an enormous number of extremely low-energy axions all occupying the same quantum state, a Bose-Einstein condensate essentially, filling the cosmos. The amount of dark matter you get from this mechanism depends on a few things, especially the Axion mass and the initial misalignment angle, where the field started before it began oscillating. For a wide range of Axion masses, typically somewhere around 1 to 100 microelectron volts, you can get exactly the right amount of dark matter to match what Planck observes. So the Axion doesn't just solve the strong CP problem, it hands you a dark matter candidate for free. 2 problems, 1 particle. That's the kind of economy that makes physicists sit up straight. But of course, a beautiful theory is just a beautiful theory until you can test it. And detecting axions is, to put it mildly, a serious experimental challenge. These particles are so light and so weakly interacting that they pass through ordinary matter as if it weren't there. But there is a handle, one precious interaction that gives experimentalists something to work with. In the presence of a strong magnetic field, an axion can convert into a photon, a real, detectable photon. This is called the Primakov effect, and it's the basis for almost every axion detection experiment that's been built or proposed. The most famous of these is ADMX, the axial dark matter experiment, which has been running in various forms since the 1990s at Lawrence Livermore National Laboratory and later at the University of Washington in Seattle. The basic idea is beautifully simple in concept, even though the execution is extraordinarily demanding. You take a large microwave cavity, essentially a carefully machined metal cylinder, and you place it inside an extremely powerful superconducting magnet. If dark matter axions are streaming through the cavity, which they should be since we're swimming in dark matter right here in the Milky Way, then occasionally one of those axions will interact with the magnetic field and convert into a microwave photon inside the cavity. The frequency of that photon corresponds to the axion's mass, so you tune the cavity to resonate at a specific frequency, amplify any signal with the most sensitive electronics you can build, and listen. It's like tuning a radio dial across the spectrum, searching for an impossibly faint station. You don't know what frequency it's broadcasting on, so you have to scan slowly, frequency by frequency, spending time at each one to build up enough sensitivity to distinguish a real signal from noise. The signals you're looking for are staggeringly small. We're talking about powers on the order of 10 to the minus 24 watts. That's a yoctowatt. To put that in perspective, a single firefly produces about 10 to the minus 3 watts. So you're looking for a signal roughly a sextillion times fainter than a firefly. and you have to distinguish it from the thermal noise of the cavity itself, which is why ADMX operates at temperatures close to absolute zero, using dilution refrigerators that cool the apparatus to about 100 millikelvin. ADMX has been steadily improving for decades, and by the late 2000s and into the 2020s, it reached a critical milestone. It achieved sensitivity to axions with the coupling strengths predicted by the most well-motivated theoretical models, the so-called KSVZ and DFSZ models, named after the physicists who developed them: Kim, Schiffman, Weinstein, and Zakharov on one side, Dine, Fischler, Srednicki, and Zhitnitsky on the other. These models predict slightly different coupling strengths between axions and photons, but both are within reach of current and near-future experiments. A DMX hasn't found a signal yet, but it's actively scanning through the microelectron volt mass range, and it's doing so with the sensitivity needed to either find the axion or rule out significant chunks of the parameter space. And ADMX isn't alone anymore. A whole ecosystem of axion experiments has sprung up in the last decade. Haystack at Yale pushes to higher frequencies, probing higher axion masses. Organ in Australia, CAP in South Korea, which has one of the strongest magnets in the world dedicated to axion searches, and several European efforts are all attacking different parts of the mass range, with different cavity designs and detection strategies. There's even a completely different approach called CASPER, which looks for the oscillating nuclear electric dipole moment that an axion dark matter field would induce, essentially going back to the strong CP problem itself and looking for its time-varying signature. And then there are the helioscope experiments, which take a different tack entirely. Instead of looking for dark matter axions in the galaxy, they look for axions produced in the core of the sun. The sun's interior is hot and full of strong electromagnetic fields, which means it should be producing axions via the Primakov effect in reverse, photons converting to axions in the sun's plasma. Those solar axions would stream outward and could be reconverted to X-ray photons in a strong laboratory magnet pointed at the sun. The most sensitive helioscope built so far is CAST at CERN, which used a decommissioned LHC test magnet, a 10-meter-long superconducting dipole, mounted on a platform that tracks the sun across the sky. CAST ran for over a decade and set the best limits on axion-photon coupling for a wide range of masses. Its successor, IAXO, the International Axion Observatory, is in development and will be significantly more sensitive, with a dedicated purpose-built magnet and X-ray optics borrowed from satellite telescope technology. What I find so compelling about the Axion story is how different it feels from the WIMP story. WIMPs were, in some sense, the obvious candidate. Massive particles from the energy scale that particle physicists were already exploring, detectable through interactions they already understood. The search strategy was brute force in a way. Build bigger detectors, go deeper underground, wait longer. And that approach has been heroic, genuinely heroic, but it hasn't found anything yet. The Axion, by contrast, requires a completely different experimental philosophy. You're not waiting for a rare collision. You're listening for a whisper, a coherent, wave-like signal that fills all of space. The technology is different. The mindset is different. And the theoretical motivation is, in some ways, even more compelling, because the Axion solves a real, concrete problem in the Standard Model, regardless of whether it turns out to be dark matter. But Axions and WIMPs aren't the only game in town. As the WIMP miracle lost some of its luster and the Axion gained prominence, the broader dark matter community began seriously exploring a much wider landscape of possibilities. And some of these ideas push into territory that's genuinely strange. Particles and structures that would have seemed like science fiction a generation ago. One of the most fascinating directions involves something called sterile neutrinos. And to understand why they're interesting, you need to know a little about the neutrinos we already have. Regular neutrinos, the ones we've detected, the ones we know exist, come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They're incredibly light, almost massless, and they interact through the weak nuclear force, which makes them absurdly difficult to detect but not impossible. Trillions of them pass through your body every second, most of them from the sun, and almost none of them ever interact with a single atom inside you. They're ghostly, but they're part of the standard model. They have a seat at the table. Now here's where it gets interesting. For a long time, physicists assumed neutrinos were completely massless, the way photons are. But starting in the late 1990s, experiments studying neutrinos from the sun and from cosmic ray interactions in the atmosphere discovered something remarkable. Neutrinos oscillate. A neutrino that starts out as an electron neutrino can spontaneously transform into a muon neutrino or a tau neutrino as it travels through space and then transform back again. This was confirmed by the Super Kamiokande experiment in Japan in 1998 and by the Sudbury Neutrino Observatory in Canada in 2001, and it was a huge deal because oscillation is only possible if neutrinos have mass. Not much mass. We're talking fractions of an electron volt, which is almost absurdly tiny. But some mass, and the standard model, as originally written, didn't account for that. So physicists needed to explain where neutrino mass comes from, and one of the most elegant mechanisms, called the seesaw mechanism, naturally predicts the existence of additional neutrinos. These hypothetical particles are called sterile neutrinos because they don't interact through any of the known forces except gravity. No electromagnetic interaction, no weak force, no strong force. Just gravity. They're called sterile because they're inert. They don't do anything through the channels we normally use to detect particles. And the seesaw mechanism says that the reason our familiar neutrinos are so incredibly light is precisely because these sterile partners are very heavy. It's like a seesaw. One end goes up, the other goes down. The heavier the sterile neutrino, the lighter the active neutrino. It's mathematically beautiful. But here's the thing. The seesaw mechanism doesn't specify exactly how heavy the sterile neutrinos should be. They could be extraordinarily massive, up near the grand unification scale, which would make them completely undetectable and irrelevant for dark matter. Or they could be much lighter, in the kilo-electron-volt range, the kilo-electron-volt range. And if they're in that sweet spot, they could be produced in the early universe in just the right abundance to account for dark matter. A sterile neutrino with a mass of a few kilo-electron volts would be what physicists call warm dark matter. Not cold like WIMPs or Axions, which move slowly and clump efficiently, but not hot like regular neutrinos, which move too fast to clump at all. Warm. Somewhere in between. And that distinction actually matters for the structure of the universe on small scales. Cold dark matter predicts that galaxies should be surrounded by enormous numbers of small satellite galaxies, little clumps of dark matter that formed early and accumulated some ordinary matter. And we do see satellite galaxies around the Milky Way, but for a long time it seemed like we saw far fewer than the simulations predicted. This was called the missing satellites problem, and it was one of a handful of small-scale puzzles that made some people wonder whether cold, dark matter was getting the fine details wrong. Warm, dark matter, like kilo-electron-volt mass sterile neutrinos, would naturally smooth out structure on small scales because the particles move fast enough to wash out the smallest clumps. So there was a period, especially in the 2000s and early 2010s, when sterile neutrinos looked like they might solve several problems at once, explaining neutrino mass, providing dark matter, and fixing the small-scale structure issues. There was even a tantalizing observational hint. In 2014, two independent groups reported detecting an unexplained X-ray emission line at an energy of about 3.5 kiloelectron volts in observations of galaxy clusters and the Andromeda Galaxy. A sterile neutrino with a mass of about 7 kiloelectron volts could very rarely decay into a regular neutrino and a photon, and that photon would have an energy of exactly half the sterile neutrino's mass, 3.5 kiloelectron volts. The signal was faint and controversial from the start. Some groups confirmed it, others didn't see it, and there were arguments about whether it could be explained by known atomic emission lines from hot plasma. The debate went back and forth for years. More recent observations, particularly from the Hitomi satellite, which tragically broke apart in orbit in 2016 after only about a month of operation, but did collect some data, cast doubt on the dark matter interpretation, and subsequent analyses with better instruments have generally weakened the case. As of now, the 3.5 kiloelectron volt line is mostly considered unlikely to be from sterile neutrino decay, though it hasn't been completely ruled out. It's one of those signals that keeps the conversation going without ever quite delivering a verdict. But sterile neutrinos remain viable as a concept, even if that particular hint faded. And they're part of a broader lesson in dark matter physics. The field has learned, sometimes painfully, that promising signals have a way of dissolving under closer scrutiny. Which brings us to an even stranger corner of the landscape. What if dark matter isn't just one particle? What if it's an entire sector, a whole family of particles with their own forces, their own interactions, their own hidden complexity? This idea goes by several names: hidden sector dark matter, dark sectors, or sometimes the dark photon framework. And it's one of the most creatively ambitious directions in modern dark matter theory. Think about it this way. Ordinary matter, the stuff you and I are made of, isn't simple. It's not just one particle. It's quarks and leptons and gauge bosons interacting through three different forces, forming atoms and molecules and chemistry and biology. There's an entire zoo of particles, governed by a rich and complicated set of rules. So why should dark matter be simple? Why should it be just one particle that sits there and does nothing except gravitate? That assumption was always a simplification, a starting point. And as the simplest candidates have resisted detection, some theorists have started asking whether we've been thinking about this too narrowly. In a hidden sector scenario, dark matter particles could interact with each other through forces that are invisible to us, a dark electromagnetism mediated by a dark photon. Dark matter particles could scatter off each other, form bound states, maybe even form dark atoms. They wouldn't interact with our photons, our electrons, our quarks, or at least only incredibly weakly. But among themselves, they could have a rich internal life. And here's what's wild. This isn't just speculation for the sake of speculation. Self-interacting dark matter, or SIDM, was proposed in part to address those same small-scale structure problems I mentioned. Cold, dark matter simulations predict that the centers of galaxies should have very steep, cuspy density profiles, the dark matter density should spike sharply toward the center. But observations of actual dwarf galaxies and low-surface brightness galaxies often show flatter, chord profiles. The density is more uniform in the middle. If dark matter particles can scatter off each other, they'd transfer energy and momentum among themselves, smoothing out those central cusps into cores. It's like how gas molecules in a room spread out to fill the space evenly, give dark matter particles a way to interact, and they redistribute themselves more smoothly. The cross-sections needed are actually quite specific. You need roughly 1 square centimeter per gram of dark matter, which sounds like a lot if you're used to particle physics cross-sections measured in picobarns and femtobarns, but it's actually a very modest interaction rate, enough to matter over cosmological timescales, but weak enough to be invisible in most other contexts. And intriguingly, this cross-section is in the right ballpark for what you'd get from a dark photon with a mass in the megavolt to gigavolt range. Now, searching for dark photons is a real experimental program. The idea is that dark photons might mix very slightly with ordinary photons through a process called kinetic mixing. This would give them a tiny, tiny coupling to ordinary charged particles, small enough that we haven't noticed yet, but potentially large enough to detect with dedicated experiments. There are beam dump experiments where you slam a high-intensity beam of electrons or protons into a target and look for dark photons emerging on the other side. There are fixed target experiments, missing mass experiments, even searches at electron-positron colliders. Groups at Jefferson Lab, at CERN, at Mainz, at Frascati, they're all looking. So far, no confirmed dark photon signal, but the parameter space is being carved away steadily, and some of the most interesting regions are just now becoming accessible. Let me take a step back for a moment, because I think it's worth appreciating how the sociology of the field has shifted. 20 years ago, if you went to a dark matter conference, it was dominated by WIMPs. The talks were about WIMP cross-sections, WIMP detection rates, WIMP candidates from supersymmetry. Axions were a niche interest, and anything else was considered fringe. Today, the landscape is completely different. The community has diversified enormously. You'll see talks on WIMPs, axions, sterile neutrinos, dark photons, self-interacting dark matter, fuzzy dark matter, primordial black holes, asymmetric dark matter, mirror dark matter, composite dark matter. The list goes on. And this isn't a sign of confusion or desperation. It's a sign of maturity. The field has recognized that the dark matter problem is hard, that nature doesn't owe us a simple answer, and that casting a wider net is scientifically responsible. One candidate that deserves special attention is fuzzy dark matter, sometimes called ultralight dark matter. This is in some ways an extension of the Axion idea, but taken to an extreme. Imagine a particle so extraordinarily light, with a mass around 10 to the minus 22 electron volts, that its de Broglie wavelength is not subatomic, not even atomic, but astronomical. We're talking wavelengths on the order of kiloparsecs, comparable to the size of a small galaxy. At that scale, the particle doesn't behave like a particle at all. It behaves like a wave. The dark matter halo of a galaxy would be a single, coherent quantum wave function, with interference patterns and standing waves on galactic scales. Quantum mechanics, which we normally think of as governing the very small, would be sculpting the very large. And just like warm dark matter and self-interacting dark matter, fuzzy dark matter would naturally suppress small-scale structure. The wave nature of the particle would create a minimum size for dark matter clumps. Below a certain scale, the quantum pressure from the uncertainty principle would prevent gravitational collapse. So you'd get fewer tiny satellite galaxies, smoother central density profiles, and a natural resolution to some of those small-scale puzzles. The constraints on fuzzy dark matter are getting tighter, though. Observations of the Lyman alpha forest, which is a series of absorption features in the spectra of distant quasars caused by intervening hydrogen gas, can probe the distribution of matter on relatively small scales at high redshift. And those observations suggest that if fuzzy dark matter exists, its mass can't be too low, or it would have washed out more small-scale structure than we actually observe. The current bounds push the mass above about 10 to the minus 21 electron volts, which squeezes the parameter space but doesn't eliminate it. And then there's an idea that's conceptually very different from all of these, the possibility that dark matter isn't a new particle at all, that instead, what we're seeing is a sign that our theory of gravity is incomplete. This idea has a long and contentious history, and it starts with a physicist named Mordechai Milgram, who in 1983 proposed something called modified Newtonian dynamics, or MOND. Milgram noticed something peculiar about the galaxy rotation curves that Vera, Rubin, and others had measured. The discrepancy between observed and predicted rotation speeds always seemed to kick in at a particular acceleration scale, roughly 1.2 times 10 to the minus 10 meters per second squared. Below that acceleration, Newtonian gravity seemed to break down. Above it, everything was fine, so Milgram proposed a simple modification. Below this critical acceleration, the gravitational force doesn't fall off as 1 over r squared, as Newton said, but more slowly, effectively as 1 over r. It's a phenomenological rule, not derived from deeper theory, but it works remarkably well for individual galaxies. It predicts flat rotation curves without any dark matter at all, and it does so with just one new parameter, that critical acceleration, which Milgram called a zero. For a single parameter model, its success across a wide range of galaxy types is honestly impressive. It predicts correlations between galaxy luminosity and rotation speed, the Tully-Fisher relation, with striking precision. And some of those predictions were made before the observations confirmed them, which in science is the gold standard. But MOND has serious problems. It struggles with galaxy clusters, the same systems where Zwicky first noticed the missing mass problem back in the 1930s. Even with MOND's modified gravity, clusters still seem to need some form of unseen mass. And the bullet cluster, which we talked about earlier, where the gravitational lensing map is clearly separated from the visible gas, is very difficult to explain without actual dark matter particles. If gravity were simply modified, you'd expect the lensing to follow the mass you can see, which is mostly the hot gas. But it doesn't. It follows the galaxies, as if there's invisible mass traveling with them. That's a strong piece of evidence for particle dark matter and against pure modifications of gravity. There have been attempts to build relativistic versions of MOND, theories that can handle cosmology and gravitational lensing. The most well-known is TVES, proposed by Jacob Bekenstein in 2004. But these theories tend to be complicated, requiring multiple new fields, and they've struggled to match the full range of cosmological observations, particularly the CMB power spectrum, which cold dark matter fits so beautifully. More recently, a proposal called superfluid dark matter has tried to bridge the gap, suggesting that dark matter behaves like a conventional cold particle on large scales, but forms a superfluid in galaxies, and the phonon excitations of that superfluid mimic Mond-like behavior. It's creative and mathematically interesting, but still very much in the speculative stage. The honest assessment is that Mond captures something real about the phenomenology of galaxies. There is a genuine acceleration scale where things change, and that's a fact that any complete theory of dark matter needs to explain. But as a replacement for dark matter, it falls short. Most of the community treats it as a clue rather than a solution, a pattern in the data that might be telling us something about how dark matter interacts with ordinary matter, or about the physics of galaxy formation, rather than about the fundamental nature of gravity itself. So where does all of this leave us? We have WIMPs, increasingly constrained, but not dead. We have Axions, theoretically motivated and experimentally accessible in a growing range of masses. We have sterile neutrinos, dark photons, self-interacting dark matter, fuzzy dark matter, and even modifications of gravity. The menu is vast, and the experiments probing these possibilities are becoming more sophisticated every year, which brings us to something I think is genuinely exciting. The next generation of experiments and observations that are either running right now or about to come online. Instruments that might finally crack this mystery open in our lifetime. And honestly, even if you're starting to drift off right now, this part is worth letting wash over you, because the scale of what's being built and launched and planned is unlike anything that's come before in dark matter research. Let's start underground, because that's where some of the most ambitious new detectors live. Remember the xenon experiments we talked about earlier? Those tanks of ultra-pure liquid xenon, sitting deep beneath mountains, waiting for a dark matter particle to bump into a xenon nucleus? Well, the latest and largest of these is LZ, which stands for Lux Zeppelin, and it's operating right now in the Sanford Underground Research Facility in South Dakota, about a mile beneath the surface. LZ contains 10 tons of liquid xenon in its active volume. That's roughly 10 times more than its predecessor, LUX. And here's why size matters so much in this game. The bigger your detector, the more target atoms you have, and the more likely it is that one of those incredibly rare interactions actually happens inside your instrument during the time you're watching. LZ published its first science results in 2022 and has already set some of the most stringent limits ever on WIMP nucleon cross-sections for a wide range of WIMP masses. It hasn't found a signal yet, but it's still collecting data, and its sensitivity will continue to improve as it accumulates more exposure time. And LZ isn't alone. Over in China, the Panda X4T experiment at the China Jinping Underground Laboratory, which, fun fact, is the deepest underground laboratory in the world, sitting under about 2,400 meters of rock, is running a 4-ton liquid xenon detector and producing competitive results. Then there's Xenon NT at Gran Sasso in Italy, the successor to Xenon 1T, with about 6 tons of liquid xenon. These 3 experiments are essentially in a friendly race, each pushing toward the same fundamental sensitivity floor. And that floor is important because it has a name, the neutrino fog, sometimes called the neutrino floor. This is the point where neutrinos from the sun, from the atmosphere, from supernovae, neutrinos that interact so rarely with matter that we usually ignore them, start producing signals in your detector that look almost identical to what a dark matter particle would produce. Once you hit the neutrino fog, you can't just build a bigger detector to get more sensitive. You need entirely new techniques to distinguish a dark matter signal from the neutrino background. The current generation of xenon experiments will approach this boundary. The next generation aims to push into it. That next generation has a name too, Darwin, or more recently rebranded as XLZD, which stands for the Xenon LZ Darwin collaboration. The idea is to combine the expertise of all three major xenon groups into one massive next-generation detector containing somewhere around 50 to 80 tons of liquid xenon. That's an enormous leap. A detector that size would be sensitive enough to detect certain types of dark matter interactions, even through the neutrino fog, using subtle differences in the energy and direction of recoils. It's currently in the planning and R&D phase, with construction potentially beginning later this decade. If WIMPs exist at the mass scales and cross-sections that are still allowed by current data, XLZD would have a real shot at finding them. And if it doesn't find them, that itself would be a profound result. It would essentially close the door on the classic WIMP hypothesis for a huge range of parameter space. Now, while the direct detection folks are digging deeper underground, the Axion hunters are scaling up too. A DMX, the Axion dark matter experiment at the University of Washington, continues to scan through microwave frequencies, looking for that faint photon signal that an Axion would produce inside a strong magnetic field. They've been methodically working their way through the microelectron volt mass range, and they've reached the sensitivity needed to detect even the most pessimistic Axion models, the DFSZ models, in parts of that range. But the challenge is that scanning is slow. Each tiny frequency window requires extended observation, and the total mass range that Axions could occupy spans many orders of magnitude. So new approaches are being developed to speed things up. Haystack at Yale has pioneered the use of quantum squeezing techniques, essentially using quantum mechanics to reduce the noise in their measurements below what was previously thought possible. That's a genuinely clever trick. By squeezing the quantum vacuum fluctuations in their amplifier, they can scan faster without losing sensitivity. It's the kind of thing where quantum information science directly enables particle physics, which is a beautiful crossover. Then there's the broadband approach. Instead of tuning a resonant cavity to one frequency at a time, some newer experiments are trying to detect axions across a wide range of frequencies simultaneously. The BREAD experiment, being developed at Fermilab, uses a dish antenna concept rather than a resonant cavity, which could allow sensitivity across a much broader mass range in a single setup. And the DM radio series of experiments is exploring lumped circuit and resonant LC designs to probe axion masses below the microelectron volt range, where traditional cavities become impractically large. These are still relatively early-stage efforts, but they represent a real expansion of the experimental frontier. Meanwhile, up in space, things are getting interesting too. The Vera Rubin Observatory, named after the astronomer whose rotation curve measurements were so pivotal, which feels exactly right, is about to begin its legacy survey of space and time from its perch in Chile. This isn't a dark matter detector in the traditional sense. It's a telescope. But what a telescope! Its 8-meter mirror and enormous camera will survey the entire visible southern sky every few nights, building up an incredibly detailed map of how matter, both visible and dark, is distributed across the universe. It will do this primarily through gravitational lensing, measuring the tiny distortions in the shapes of billions of galaxies caused by the dark matter between us and them. This technique, called weak gravitational lensing, allows you to map dark matter's distribution in 3 dimensions across cosmic time. The Rubin Observatory will measure this with unprecedented precision, and those measurements will tell us not just where dark matter is, but how it clumps, how it flows, how its structures have grown over billions of years. And that growth rate is sensitive to the properties of dark matter itself, whether it's cold, warm, fuzzy, or self-interacting. Different dark matter models predict subtly different patterns of structure formation, and Rubin will have the statistical power to distinguish between them. And it's not working alone. The European Space Agency's Euclid mission launched in 2023 and is currently conducting its own massive survey of the sky, also focused on weak lensing and galaxy clustering. Euclid and Rubin together will give us complementary views of the same cosmic web, and the combination will be far more powerful than either alone. Think about what that means. We're building a three-dimensional map of the invisible scaffolding of the universe, using the light of distant galaxies as our probe. That's happening right now. There's also the CMB, which keeps giving. The Simons Observatory in Chile's Atacama Desert is deploying a new generation of microwave telescopes that will measure the cosmic microwave background with far greater sensitivity and angular resolution than even Planck achieved. And beyond that, the CMBS-4 project, Stage 4, is planned as a massive ground-based effort with hundreds of thousands of detectors spread across telescopes in Chile and the South Pole. CMBS-4 will be sensitive enough to detect or rule out certain light relic particles, including some sterile neutrino models, by measuring the effective number of neutrino species with extraordinary precision. It could also detect the gravitational lensing of the CMB by dark matter structures with enough detail to constrain dark matter's properties in ways we can't currently access. And here's something I find quietly thrilling. Gravitational wave astronomy is entering the picture too. LIGO and Virgo have already detected merging black holes and neutron stars, but the next generation of gravitational wave detectors, the Einstein Telescope in Europe and Cosmic Explorer in the US, both planned for the 2030s, will be sensitive enough to potentially detect primordial black holes if they exist in certain mass ranges. Remember, primordial black holes are one of those dark matter candidates that doesn't require any new particles at all, just black holes formed in the very early universe, before stars even existed. If dark matter is partly or entirely made of primordial black holes, gravitational wave detectors might find them through their mergers, or through the subtle gravitational effects they'd have on other signals. It's a long shot, but it's a real observational channel that didn't exist a decade ago. So you can see the pattern here. The search for dark matter has expanded from a few pioneering experiments into a global, multi-messenger, multi-technique enterprise. Underground detectors hunting for direct nuclear recoils, microwave cavities and quantum sensors hunting for axion conversions, particle colliders hunting for missing energy, telescopes mapping gravitational lensing across billions of light years, satellites measuring the cosmic microwave background to parts per million, gravitational wave observatories listening for the ripples of merging compact objects. Each of these approaches is sensitive to different dark matter candidates, different mass ranges, different interaction strengths, and they're all getting better at the same time. But here's the thing that I think really matters, and it's something worth sitting with as you settle deeper into wherever you are right now. Despite all of this extraordinary effort, decades of work, billions of dollars, some of the most sensitive instruments ever constructed by human beings, we still don't know what dark matter is. We know it's there. The evidence is overwhelming, and comes from so many independent lines that denying its existence requires you to believe in an almost absurd conspiracy of coincidences across completely unrelated physical systems. But its identity remains hidden. And that's not a failure of science. That's science working exactly as it should, honestly and patiently, refusing to declare victory until the evidence is truly in hand. The universe is under no obligation to make its secrets easy to find. And there's a deeper question lurking beneath all the experimental progress, one that some physicists are starting to ask more openly. What if dark matter doesn't interact with ordinary matter through any force except gravity? What if there's no nuclear recoil to detect, no axion to photon conversion, no annihilation signal, no missing energy at a collider? What if dark matter is, in a very real sense, truly dark, gravitationally present, but otherwise completely decoupled from everything we can touch and measure? That would be a profound challenge. Maybe the most profound challenge physics has ever faced. Because if dark matter interacts only through gravity, then the entire experimental program we've been talking about, every detector, every cavity, every collider search, is looking for a signal that simply isn't there. Not because the instruments aren't sensitive enough, but because the interaction itself doesn't exist. Let that idea sit for a moment. It's a strange one. We're so used to the assumption that if something is real, if something is physically present in the universe, then there must be some way to poke it, prod it, bounce something off it, make it reveal itself through some channel other than the gentle, patient tug of gravity. But gravity is the weakest of all the forces, absurdly weak. The electromagnetic force between two protons is something like 10 to the 36th times stronger than the gravitational force between them. That's a 1, followed by 36 zeros. Gravity is so feeble at the particle level that we can barely detect it between individual objects in a laboratory, let alone use it to identify what a single dark matter particle is made of. And yet, gravity is the only reason we know dark matter exists at all. Every piece of evidence we've talked about tonight, Zwicky's galaxy clusters, Rubin's rotation curves, the bullet cluster, gravitational lensing, the acoustic peaks in the cosmic microwave background, the large-scale structure of the cosmic web, all of it, every single line of evidence comes down to gravity. Dark matter pulls on things. It bends space-time. It clumps and clusters and shapes the universe. But it has never, not once, been caught doing anything else. Now, most physicists don't think we're in that worst-case scenario. Not yet. There's still plenty of parameter space to explore, plenty of candidates that haven't been ruled out, plenty of clever new detection strategies being developed. The game isn't over, but the possibility that it could be purely gravitational is no longer something people dismiss out of hand. It's become part of the conversation. And honestly, I think that's healthy. It keeps everyone honest. It forces the field to think harder about what we can learn from gravity alone and whether there are ways to narrow down dark matter's identity, even if we never detect it in a laboratory. And here's where things get genuinely interesting, because it turns out there's quite a lot you can learn from gravity if you're clever enough about how you look. Think about what the next generation of surveys is going to do. The Vera Rubin Observatory, which we talked about, is going to map the positions and shapes of billions of galaxies. Euclid, already in space, is doing something similar from above the atmosphere. The Nancy Grace Roman Space Telescope, planned for the mid-2020s, will add yet another layer of precision. Together, these instruments are going to create three-dimensional maps of how dark matter is distributed across the observable universe, not by seeing dark matter directly, but by measuring how its gravity distorts the light from background galaxies. Weak gravitational lensing, remember? That subtle statistical warping of galaxy shapes that tells you where the mass is, even when you can't see it. Here's what's really clever about this approach. Different types of dark matter produce different patterns of structure. Cold dark matter, the heavy, slow-moving kind, like classic WIMPs, clumps very efficiently. It forms dense, compact halos around galaxies, with lots of small substructure. Little satellite halos orbiting within bigger ones, dense cores at the centers of galaxies, a whole hierarchy of nested gravitational structures. Warm dark matter, which moves faster and has lower mass, like a sterile neutrino in the kilo-electron-volt range, smooths things out. It can't clump as tightly on small scales because the particles were moving too fast in the early universe to get captured by small gravitational wells. So you get fewer satellite galaxies, smoother halo profiles, less substructure. Fuzzy dark matter, those ultralight particles with enormous quantum wavelengths, smooths things out even more dramatically. And self-interacting dark matter changes the internal structure of halos. It creates softer, more core density profiles instead of the sharp cusps that cold dark matter predicts. So even without ever detecting a dark matter particle in a lab, you can potentially figure out what kind of particle it is, or at least narrow down its properties, by mapping the structure of the universe with enough precision. You're using the entire cosmos as your detector. The distribution of galaxies, the shapes of dark matter halos, the number of satellite galaxies, the density profiles at the centers of clusters. All of these are imprints of dark matter's particle physics, written in the language of gravity. And the surveys coming online right now are reaching the sensitivity where these distinctions start to matter. We're not just asking, is dark matter there anymore? We're asking, how does it behave on scales of a few thousand light years? That's a much more specific question, and the answer has real power to discriminate between candidates. There's another gravitational tool that's becoming increasingly important, and it's one that would have seemed like pure science fiction not that long ago. Gravitational waves. We talked about how Einstein Telescope and Cosmic Explorer could potentially detect primordial black holes if they exist in the right mass range. But gravitational waves can tell us about dark matter in other ways too. If dark matter forms dense concentrations around black holes, what some theorists call dark matter spikes, then when two black holes spiral together and merge, the dark matter environment could leave a subtle imprint on the gravitational wave signal. The inspiral might happen slightly faster or slower than you'd expect in a vacuum, because the dark matter is exerting a tiny drag or altering the orbital dynamics. These effects are incredibly small, but the next generation of detectors might just be sensitive enough to see them. It's a beautiful idea, using the collision of black holes to probe the invisible medium they're swimming through. And then there's something even more speculative, but deeply fascinating. Some theorists have proposed that if dark matter has any self-interactions at all, even incredibly feeble ones, it might form its own structures. Not atoms, not molecules, nothing as complex as ordinary matter. But perhaps dark matter could form thin disks within galaxies, or dense clumps, or even exotic objects that we haven't imagined yet. A whole shadow universe of structure, invisible to us except through its gravitational effects. This idea goes by various names: shadow sectors, mirror matter, dark complexity, and most of it is highly speculative. But it's not crazy. There's no fundamental reason why dark matter has to be simple. We assume it's simple, because that's the easiest thing to model, and because the cosmological data, so far, is consistent with simplicity. But the data is also consistent with a moderate amount of complexity, as long as the overall gravitational behavior matches what we observe. So, here's where we stand. And I think this is actually a remarkable place to be, even if it doesn't feel like the triumphant resolution we might want. We know that roughly 27% of the universe's total energy content is dark matter. We know this from multiple independent lines of evidence that all agree. We know dark matter is not made of any particle in the standard model of particle physics. It's not protons, neutrons, electrons, neutrinos, or photons. It's something new. We know it interacts gravitationally, and we know it played a crucial role in shaping the universe we see today. Without dark matter, galaxies wouldn't have formed, stars wouldn't have ignited, planets wouldn't exist, and you and I wouldn't be here having this conversation. In a very real sense, dark matter is the scaffolding on which everything visible was built. But we don't know what it is. And that gap between knowing something exists and knowing what it is, that gap is where some of the most exciting science of the 21st century lives. Think about how many times in the history of physics we've been in a similar position. In the mid-1800s, astronomers noticed that the orbit of Uranus didn't quite match what Newton's laws predicted. Something was pulling on it, something invisible. They could have said the laws of gravity were wrong. Instead, a few mathematicians, Urbain Le Verrier in France, John Couch Adams in England, sat down and calculated where an unseen planet would have to be to produce the observed perturbations. And when Johann Galle pointed his telescope at the spot Le Verrier predicted, there was Neptune, an entire world, discovered not by seeing it, but by noticing its gravitational pull on something else. That's essentially what Zwicky did in the 1930s, what Rubin and Ford did in the 1970s, what every dark matter observation has done since. We're seeing the gravitational pull. We just haven't found our Neptune yet. But there's also a cautionary tale in that same history. Before Neptune was discovered, Le Verrier also noticed anomalies in the orbit of Mercury, a slow precession of its perihelion that Newtonian gravity couldn't explain. He proposed another unseen planet, even closer to the Sun, which he called Vulcan. Astronomers searched for it for decades. They never found it, because it wasn't there. The real explanation turned out to be something far more radical. Einstein's general relativity, a completely new theory of gravity that predicted exactly the right amount of precession without needing any hidden planet. So sometimes the invisible thing, pulling on what you can see, is a new object. And sometimes it's a sign that your understanding of the fundamental laws needs to change. That's the tension at the heart of the dark matter problem. Most physicists believe it's a particle, a new kind of matter, waiting to be found. And the evidence strongly supports that view. The bullet cluster, the CMB acoustic peaks, the large-scale structure, these are very hard to explain without actual dark matter particles. But a small minority of researchers keep pushing on the other possibility, that our theory of gravity is incomplete, that something about how gravity works on large scales is different from what we expect. MOND and its relativistic extensions haven't been able to match the full range of observations, as we discussed. But the fact that Milgram's simple formula works as well as it does for galaxy rotation curves, that's still a puzzle. Even if dark matter is real, there might be something about the interplay between dark matter and ordinary matter that produces that MOND-like behavior, and understanding why would teach us something deep. Science is comfortable with not knowing. That's something that can be hard to appreciate from the outside, where results are expected to be clean and final. But inside the practice of science, uncertainty is the fuel. Every unanswered question is an invitation. Every null result, every experiment that doesn't find what it was looking for, is still a result. It tells you where the answer isn't, and that narrows the search. The fact that LX and Xenon and Pandiax haven't found WIMPs doesn't mean the experiments failed. It means we now know with extraordinary precision that if WIMPs exist, they interact with ordinary matter even more weakly than we hoped. That's real knowledge. That changes the theoretical landscape. That guides the next generation of searches, and the next generation is coming. XLZD, with its 50 to 80 tons of liquid xenon pushing toward the neutrino fog. DM radio and BREAD scanning new swaths of Axion parameter space. CMBS4 measuring the cosmic microwave background with such precision that it could detect the gravitational influence of particles that haven't interacted with anything since the universe was a second old. The Vera Rubin Observatory, mapping the dark matter skeleton of the cosmos galaxy by galaxy. Gravitational wave observatories listening for whispers from the dark sector. All of these are going to come online in the next 10 to 20 years. And any one of them could be the experiment that cracks it open. Or none of them might. And that would be okay too. Because it would mean the universe is even stranger and more surprising than we thought. And we'd have to think harder, build new tools, ask different questions. That's how it's always worked. That's how we got from Galileo's telescope to gravitational wave detectors, from Faraday's coils of wire to the Large Hadron Collider, from wondering why the stars shine to understanding nuclear fusion. The arc of physics bends toward understanding, but it bends slowly, and it never follows the path you expect. So as you lie there, maybe drifting now, maybe already half asleep, here's what I want you to carry with you into whatever dreams are coming. You live in a universe where 85% of all the matter is invisible. It doesn't glow, it doesn't absorb light, it doesn't bump into atoms in any way we've been able to measure. But it's everywhere. It's in this galaxy, right now, a vast halo of the stuff extending far beyond the visible stars. Some of it is probably passing through you at this very moment, streaming through your body without disturbing a single atom, as indifferent to your existence as you are to its. And yet without it, none of this would be here. No Milky Way, no solar system, no Earth, no you. We're made of the rare stuff, you and I, the ordinary matter, the 5%, the luminous fraction, and we're using that tiny sliver of the universe's material to try to understand the rest of it. That's an extraordinary thing when you think about it. A small collection of atoms, arranged just so, on a small planet, orbiting an ordinary star, in one galaxy among trillions. And those atoms have figured out that most of the universe is made of something they can't see, and they're building instruments to find it. Whatever dark matter turns out to be, a WIMP, an axion, a sterile neutrino, a primordial black hole, something we haven't even imagined yet. The story of how we figured it out will be one of the great stories in the history of science. And you've just heard the first 80-some years of that story. From Fritz Zwicky squinting at galaxy clusters in the 1930s, to quantum-squeezed microwave cavities and 50-ton xenon detectors in the 2020s. The next chapter hasn't been written yet. But somewhere tonight, in a lab deep underground, or in a control room beside a telescope, or at a desk covered in equations, someone is working on it. And one of these nights, maybe soon, maybe not for decades, they're going to find the answer. And when they do, it'll change everything we thought we knew about what the universe is made of. But that's a story for another night. For now, just rest. Let the ideas settle. Let the universe be mysterious for a little while longer. It's waited 13.8 billion years. It can wait one more night, and so can you.